There it goes. All right, cool. 25 is, let me read out loud to you guys. It says you're draining a tank and it takes 12 hours to drain the tank. And it says opening the valve at the bottom. So we've got, I don't know what kind of tank it is. It's just a tank. And there's like a little spigot thing here. And there's fluid coming out of it. And it takes 12 hours to drain this tank. The depth of the fluid in the tank after T hours after the valve is open is modeled. So there's some fluid in here, okay? And it's coming out of the tank. And the height, y, is modeled by the following equation, which is y is equal to 6 times 1 minus t over 12 squared meters. So that's the height of the volume of the tank. Okay? And then what it wants us to find for part A, it says find dy dt. Okay, and so we'll start there. So now let me, and I had this conversation with another student yesterday. Remember that derivatives, when we're asked to take the derivative of something, there's lots of ways they can ask us derivative. They could say y prime. They could say f prime of x. They could say f prime. They could say d dx, which means take the derivative with respect to x of y. They could say take the derivative with respect to x of f. Or you could see it like this, dy dx, or you could see it like this, which is df dx, right? There's a couple other ways. And sometimes when we use u substitution, we might do something like this, where we'll say u prime or u of x prime, or we'll say v prime or v of x prime. So there's lots of ways that you could write it. And the reason there's a couple different ways is that Newton and Leibniz, they both kind of developed calculus at the same time, and one uses one notation and the other uses the other. Some other key words that you might want to think about too is when you hear tangent, just know that the tangent line has the slope, which is the derivative of the original curve. Another word would be like instantaneous rate of change is another kind of thing. And so what we're really looking for is the rate of change in which this thing comes down, okay? Because that helps us to determine how the water changes out of the tank. And so to take the derivative of this is a little messy. It's just a little messy, but it's not that hard. We have a couple of constants in the front, and there's lots of ways you could do this. I'm not quite sure. Probably what I would do first before I take the derivative of this thing is I would go through and push, I'd expand some things and multiply it out and see what I get. So the first thing I would do is I would say that y is equal to, and I'm going to, over here to the side, I would say 1 minus t over 12. Oh, yeah. And times 1 minus t over 12, like that. And then FOIL that out. So I'm going to FOIL this out. And then multiply it by 6. So I get 1 minus t over 12, minus t over 12, and then a positive t squared over 144. So I've got 6 times 1 minus, what is that, 2t12? 2t over 12, which will reduce down to something else in a second. T squared over 144. Now this reduces down to 1 over 6, doesn't it? So now when I push the 6 through, what I end up with is 6, right? 6 times 1 is 6. But what's 1/6 of 6? 1, or negative 1. Don't forget my negative sign. So I've got negative t here. And then 6 over 144, let's write that out. I think that reduces. In fact, I know it does. Okay, you guys with me so far? Any questions? You understand what I'm doing? Now, how many times does 6 go into 144? Is it 24 times? Yeah. So I've got 6 minus t plus t squared over 24. Okay, so now I need to take the derivative of all that. So y prime then would just be, this goes away, this becomes -1, and then if I toss the 2 in the front, I've got positive 2t all over 24. And the reason I do that is we could think of this as t squared times the quantity 1 over 24, or 1 over 24 times the quantity t squared. And so since this is a constant multiplier, it just stays in there. So y prime then, if I wanted to clean this up, would be t over 12 minus 1 if I wrote it in descending order. Does that seem right? I'll leave that up there for a second so you could let it soak in. So I think this is my rate of change. Now what we see is as t increases, right, the height, so as time, over time, as the time increases, what happens to the rate in which the tank empties, or it appears the height changes? That increases as well. Okay, so let's write that down. We said that dy dt, which is the same as y prime, is just going to be t over 12 minus 1, right? That was what we said, part A. Okay, cool. Now for part B, what they asked for was the fluid level is falling fastest when dt is the most negative. Right? Well, let me state the question. I said the answer. Let me state the question. B says, when is the fluid level of the tank falling the fastest? When is it falling the slowest? And what are the times? So when is this thing falling the fastest? Well, we got to think about this. Based on dy dt, it's the fastest when dy dt is the most negative. Now t represents time, so I'm never going to have a negative value for t. So if I let t equal 0, what is dy dt? -1. If I let it become 1 second later, I've got 1 over 12 minus 1. What's that? It's more than -1, right? Because I'm adding something to it. So as time increases, I guess what I'm trying to say is that this is, dy dt has its lowest value when t equals 0. Does that make sense? So I said earlier, it seems like when you look at the graph, it seems like as time increases, that's when the rate of change is the highest, but I kind of had it backwards, right? And that was the point. It's counterintuitive. We had to think of that through mathematically. And so when is it falling the slowest? Well, following that same logic, when would it be the slowest? Which would be what? I'll give you a clue. When does dy dt equal 0? No. When does dy dt equal 0? 12. So just to kind of recap, because I see some blank faces there, you guys got that look on your face. It's the fastest when t equals 0, and it is the slowest when t equals 12. Because this is the rate of change. This is and we want that value to become, we want a negative value. Do you guys understand that? When we think of rates, we always think of rates as increases. But how should we think of these rates? The water coming out. We're decreasing the water level, so we need to think in terms of decreasing rates, which means we need to think of negative rates. I don't want a positive rate. In other words, based on this mathematical model, when we get past 12 seconds, my rate of change will be positive, which means I'm increasing water. Right? Now I can plug in some numbers and get some number values, but we know at some point in time this thing's going to run out of water. Okay?
Well, I guess you could.
What? Yeah.
Why is it the slowest at t equals 12?
Huh?
Why is it the slowest at t equals 12?
Well, it's the slowest. It's okay. So let's talk about that. That's a great question. dy dt is t over 12 minus 1. Now we just said that we're talking about water draining out of this tank. That means that it's going to decrease. That means that the height is always going to decrease, or it should be negative. So my rate of change should be negative, right? So if you look at this quadratic equation, it's basically, well, we could graph it in a second, but we want, this thing is, the volume of this tank is draining, or the height of the water level or fluid level is at its most when dy dt is the most negative, okay? And we said that that occurs because when t equals 0, we get -1. That's the most negative it'll ever be, because t is time, right? And so we're going, t has to be greater than or equal to 0. So now when is it the slowest? Yeah, when it's 0, because I can't have a positive value because it's not filling the tank with water. I mean, mathematically, I could plug in any number I wanted to, and I'll get a solution, right? But those are extraneous values. So what I'm going to look at is dy dt, and that occurs at 12. So when t equals 12, I get 1 minus 1, which is 0, which is the closest I can get to a positive number. Now what is that saying? That's saying that the change in the water level is at 0. That occurs right before the last drop of water falls out of that tank. Does that make sense? Okay? Or as the last drop of water falls out of the tank, it changes 0 amount. And so that's when it's the slowest, and that occurs when t is equal to 12. Okay? And then we just had to think that through. Now for part C, so far we're doing good. Part C is the last question for this example, and it says graph y and dy dt together and discuss the behavior of y and its relationship of signs and values to dy dt. So I'm going to do this on my graphing calculator, but I'm going to use the one on my website because I like, well, which one will be better? No, I'll do it on my graphing calculator. So remember that y, what did we say the long version or the expanded version of y was?
Thank you.
It was 6 minus t plus t over t squared over 24, right?
Yeah.
And then we said that y prime was just T over 12 minus 1, right? Did I do that right? My T looks a little funny. Is that right? I'm only writing it that way because it's a little easier to put in the calculator. So let's fire up the calculator and see what it does. Now this is probably one of the, I have to be honest with you, trying to establish or determine the relationship between the graph of the function and its the graph of the derivative. It's important, but it's kind of hard to like figure it out at first. So if let's graph this first. So I've got 6 minus x plus x squared divided by 24. And I don't know where that looks on the graph. We'll probably have to zoom out a little bit. All right, so that's what it looks like. That's the graph. And so what we're looking at here is this represents the height of the tank. So when x equals 0, which represents time, the height of the tank is 6 meters. Do you guys see that? 1 second later, the height of the tank is 5 meters. At 2 seconds, the height of the tank is about 4 meters. At 3 seconds, it's about 3.375 meters. At 4 seconds, it's 2.66 meters. And when did we say it was at its lowest amount? At 12. You guys see that? Does that make sense to you guys?
I was supposed to take 12 hours, not 12 seconds.
Oh, it might have been hours. Yeah, I can't remember the units. It's probably hours. It's probably hours. So, but it's time. 12 units of time, right? Now, let's look at the derivative of this. So now, as you can see mathematically, I've used this model, but at 13 seconds, what happens to the water level using this mathematical model? It starts filling back up. Is that a reality? No, not really. Okay. So, but this model worked perfect to demonstrate the value of the height of the tank. So now when I go to graph this thing, if I take the derivative, y prime was actually x divided by 12, and then we subtracted 1 from it, right? So now we're going to graph that. And so what we see here is at x equals 0, and I'm going to change my value, my other one. What we're seeing is that the decrease in height is about 1 meter per hour, because that's what y represents, is the decrease. Now what that means is that the slope of this graph is negative 0.98. If we go 1 second later, now the decrease or the slope of the curve is negative 0.92, roughly, if we were to approximate. At 3 seconds, the decrease is 0.75, negative 0.75. So it's decreasing at this. In other words, if I were to take an average, right after 3 hours, my height of the volume of fluid in the tank would be decreasing by about 0.75 meters per hour. Does that make sense to you guys? And so what we notice is at 4 seconds, the rate decreases less. Whoops. And then at 5 seconds, or 5 hours, I'm sorry, it decreases less and less and less. And so finally at 12 seconds, what is my rate of change? 0. Why? Because there isn't a drop of water left in the tank. So what does that mean? Well, what that means is, if I look at the table of values, this is how much the height of the fluid in the tank. This is the rate in which it decreases, actually, because it's a negative value. After 1 hour, this is the height of the tank, which means it decreased by this much in 1 hour. After 2 hours, this is the height in the tank, and this is the rate in which it decreases. Does that make sense? Now, how do I put that into words for part C? Part C, again, said graph the two and to discuss the behavior. Well, if I were to write that down in words, I would say that over time, the rate that the height changes decreases. And at 12 hours, because I think he was right, I think it was in hours, we run out of water. So y prime equals 0 and y equals 0. So once we run out of water, that's it. Now t greater than 12 doesn't matter, or something along those lines. Does that make sense to you guys? Okay. And so that's what engineers use calculus for.